Here we're going to explore work done by a specific force called gravity, and or in this case, really, it's weight. And this is going to be one of the places where this process of using work and kinetic energy can really start to save us time and simplify things for us. Okay, and so we're going to start with a simple question. Okay, so let's say that there is a block. Okay, or let's say there's an elevator, and this elevator has a mass of 500 kilograms, and let's say that it's being lifted up at a rate of 3 meters per second, so it's moving up at a constant speed. Okay, and let's say that we lift it up for maybe it gets raised up 3 meters. Let's use a different number. Let's get raised up 4 meters. Okay, so we got this elevator gets raised up 4 meters at a constant speed. And so the question is, so this is a cable here, right, that's holding it in place. And I want to know the work done by gravity. Oops, something happened there. And the work done by tension from the cable. Okay? So we'll start with work from gravity. Okay? So let's draw even a free body diagram. So we have the weight, and we have the tension pulling up, and these are balanced. And the reason we know they're balanced is because we said it was pulling at a constant speed. Okay? Well, so then the work done by gravity would be equal to the force of gravity times the displacement times the cosine of the angle between them. Okay, and so in this case, the force of gravity is its weight, mg. The displacement would be 4 meters. And then the angle, since weight is pulling down and it's getting pulled up, the angle there is going to be 180 degrees. So cosine of 180 is -1. Okay, so if we multiply all these together, we'll just use 10 for g. So that's 500 times 10 times 4 times -1. We're going to get negative 20,000 joules, or negative 20, we'll say kilojoules. Okay. And so what that means is that the work done by gravity, so the elevator's going up, so elevator's moving up, but gravity is pulling it down. Since they're acting in the opposite direction, the gravity, the weight, is taking energy away. If there's no weight there and just the pull of tension, then the velocity would be increasing, kinetic energy would be increasing. Since this downward force is balancing it out, as tension adds energy to the elevator, weight is taking energy away. Okay? And so we get negative kilojoules of work done by gravity. And so if we want to find the work done by tension, we can say that the total work is equal to the change in kinetic energy. The change in kinetic energy is 0 because the final and initial velocities are the same. And so it's going to be equal to the work from gravity plus the work from tension. Well, if gravity did negative 20 kilojoules, okay, then when we solve this, we're going to get that tension did 20 kilojoules of work. Okay? And so if we add those together, the total work done is 0 because they balance out. And negative 20 kilojoules of work were done by gravity, and 20 kilojoules of work were done by tension. Okay? Okay, so I'm going to show you another example where we have a block sliding down a ramp. Okay, the ramp is at a 30-degree angle. The block has a mass of 2 kilograms. We're going to say it starts sliding from rest. And for this one, we'll say that it's a frictionless ramp, and it starts from a height up of 0.4 meters. Okay, now before we get into this, this is a place where it's going to get a little bit confusing, but also using work here can make this much simpler than what we would have done before, because we did this in class and we had to find acceleration down the ramp and then to find the speed at the bottom of the ramp, we had to do like kinematics. We had to figure out how far down the ramp it had to go and stuff like that. Using work, we can do this in a much simpler way. Okay, and so let's first say that the block is going to slide a distance. Call this distance d, and to find this, we'd have to use trig. We know the angle is 30 degrees, and we know the height is 0.4, and so we can use sine and SOHCAHTOA and say that distance would be equal to, it would be the hypotenuse, or it would be 0.4 meters divided by sine of 30, since this is the hypotenuse. Okay? Now, when we set this up, what we're going to realize is there's a much simpler way of doing this. Okay, so we can say, if we want to use work to find how fast it's going at the bottom of the ramp, we could say the work done, let's draw free body diagrams. We have weight and normal force, right? And so what we can do is we could say, okay, the work done by gravity is the work done to pull it down the ramp. And so this component of gravity is mg cos theta, okay, and it's 30, I believe. Or this was, sorry, sine 30, I apologize. So we could say, okay, so the work by gravity is equal to this displacement, or the force down the ramp, mg sine 30, times the displacement, which is 0.4 meters over sine of 30. Okay? Now what you'll notice is, in this equation here, sine of 30 is going to cancel out and divide to be 1. And so we get that it's equal to mg times 0.4 meters. Okay? This is a multiplication. Alright, and so basically, if you multiply the amount of weight times the total height here, you're going to find the amount of work done by gravity as it slides down the ramp. Okay? Now, the reason why this works is because, remember, the definition of the work is to find the amount of force and multiply it by the parallel displacement. Okay? Well, when this block slides down this ramp, it experiences a perpendicular displacement and a parallel displacement. Okay? The perpendicular, right, because gravity is this way, it moves this way and this way. So gravity has no effect on displacement this way. It does have effect on displacement this way. Okay, so what we can do is, if we use just this displacement that's parallel to the force of gravity, we can then go ahead and use that to calculate the amount of work done. Okay, and as I said, this is kind of confusing to grasp. Basically, we're saying that instead of having to do this work to manually calculate the components that are parallel, we can just recognize that this is parallel to that downward force and multiply them together. Okay? And so that's basically what we've done here. So when we're doing work from gravity, it's actually just equal to the amount of weight from something times the height that it's changing. So we'll say, for height, we'll use delta y. Okay? So however far it rises or falls. Okay? And so that is work from gravity. And so I hope now that you can connect this back to the question we did in class and see how this could save us a lot of time, okay, in figuring out things such as, like, if it's going to continue going, where it's going to slide to a stop and stuff like that. Okay, we'll do one more example like this, hopefully to help you get some practice with it. So here we have a scenario where there's an elevator similar to the one before. It has a mass of 500 kilograms, and it's accelerating downward. So it's connected, but it's slipping. And so it's slipping, it's kind of falling. It's going to fall 12 meters as it slips. And as it slips, it has an acceleration of g over 5. Okay, so 1/5 of g, or about 2 meters per second squared. Okay, and so the question is, there's a couple things we want to find. We want to find how much work is done by gravity here, and what is the strength of the tension in that cable. Okay, and so we have to kind of think about this from a different way here, because we're given acceleration and we're given some quantities as far as like displacement and initial velocity goes. And so one of the ways that we can start here is by focusing on our acceleration. Okay, so we know that we have acceleration here of g over 5. Okay, we know we have a displacement, and we know that we have an initial velocity. So with these three quantities, we can actually find the final velocity. Okay, another approach we could take is that we can find the work done by gravity because we know what the weight is. The weight in this case is the mass of 500. Okay, and acceleration of 9.8, or the strength of gravity, I guess. And then we can multiply this by the displacement of 12 meters. Okay, and then since this and this are in the same direction, it's positive. Okay, and let's actually, instead of use 9.8, let's use 10. So this is going to give us 5,000 times 12 is going to be 60 kilojoules of work done by gravity on this elevator. Okay, and so then we can say, okay, from here I can start exploring maybe the total work. And so I can say, okay, maybe in order to do that I need to find out how fast it's moving at the end. Okay, and so I'll use kinematics. I can use this equation right here. Okay, and when I solve this, I'll plug in 2, 12, and 4. Okay, and so using that, I find that my velocity at the end is 8 meters per second. And so I can say, okay, well, I know the velocity before and after now. I can think about using change in kinetic energy. So my goal here is to find tension. I can say, okay, the work done by gravity plus the work done by tension. So this is the total work done over here on the left. Okay, that's going to be equal to the change in kinetic energy, which is 1/2. I'm going to factor out 1/2 and m to make things a little bit easier. So 1/2 times 500 times the change in velocity squared. So that would be 8 squared minus 4 squared. Okay, I also know that the work done by gravity is 60 kilojoules, or 60,000 joules. And so now I can go ahead and actually solve for the work done by tension. And we get negative 48,000 joules, or negative 48 kilojoules. So what that means is that tension is doing negative work. So you could think about this if if there was no tension there, then by the time it was done falling, it would have 60 total kilojoules of energy. But because tension is interfering with the fall, then it's doing negative 48 kilojoules of work. And so at the end, we have a net energy of, or we have a net, I guess, change of energy. Sorry, this would be the change. So if it was just gravity, the kinetic energy would change by 60,000 joules. Because tension was there, it kind of did 48,000 joules of energy upward. It was taking 48,000 joules of energy away, and so at the end, the energy only increased by about 12,000 joules. Okay? The last question here was to find the tension, and so we could say, well, if the work from tension was negative 48 kilojoules, well, work is equal to the force, in this case tension, times the displacement, which was 12, and it would be times negative 1 because they're at opposite directions. Okay, and so the displacement here would be 12 meters, and this is 48,000 joules, or 48 kilojoules. And so when we divide that over, we get that tension was equal to about 4,000 newtons. Okay?